science and deep learning background, so please be easy on me, especially on the terminology. So this is not an introduction talk. This is about a very specific work we had with Ashish on a data-driven attack to transient hunting or transient detection on images. So what is it about? So basically, input-output speaking, so the input is a reference image and a science image, or maybe you call it template image and science image. And the output would be a very clean image, a blank image, only having the transient in it. So this is my way of defining detection for this task. And one terminology note is that detection, I mean, where I come from, was usually defined as localization plus classification. So we need to also localize the object in the image. It's not the case that the transient is at a fixed position and you just need to say if it is a valid transient or not. So this is the definition of the task. So the mathematical formulation. Actually, this is very important. It's not like that anyhow that you define it, the network will be able to solve it. We actually saw it yesterday together that with a slight perturbation into the mathematical formulation, the network was failing to learn. So we have one image from one region of the sky and another image, I2, which is supposed to be from the same region, plus this image, which is supposed to be a blank image with a transient in it. So the problem looks to be very easy to attack, right? So I2 minus I1 should be the answer. Well, it turns out that's not the case because each image is convolved with a randomly selected or a random PSF or kernel. Also, and the phi1 and phi1 and phi2 are different. Also, a sky level and a noise is added to the background or to the whole image, which are different in the two instances. And let's not forget about displacement or unregisteredness of the images. So these two images are supposed to be of the same regions of the sky, but usually they are not. So they may be 1 pixel off or rotations be there. And what we are looking for in this definition is IT, which is the transient image in the space of the second image. So IT convolved by phi2. This could be also defined differently, but this is how we chose it, to also resemble the PSF matching things that are being tried to attack in the community. So why do we do this with deep learning? The answer is clear, because deep learning is cool. Well, yes, but there are other reasons too. So this is how you would attack this problem, such a problem in traditional pipelines. It would be really a pipeline, a big pipeline, which is composed of registration, denoising, PSF matching, subtraction, to name only the main ones. And if you do all these correctly, you get such a thing. This is a result from one of the state-of-the-art methods, which uses non-deep learning methods. So you see that we have a lot of noise here and a lot of false positives here, while we were really looking only for this transient. So we propose an end-to-end solution to this problem. The network receives the pair of images and gives us the clean image without any noise to tackle all the components together. And of course, we got like 10 milliseconds per sample, and we didn't even try to make it fast. So it's already quite fast. So a quick history on the architecture, where it comes from. So this is my recent work, not recent work, relatively recent work on domain adaptation using multitask learning. And I borrowed the architecture from this part of the work. So basically an encoder and a decoder, that's it. So here's a detailed representation of it. So an encoder-decoder network, very quickly, is a set of a sequence of convolutional layers followed by up-convolutional layers, which take the image to a low-dimensional space, in a spatial dimensions, I mean, and then take it up to the original size. And this output is supposed to be our transient image, basically. So we also have multi-scale loss here, such that we penalize the network even if there is a slight difference in the lower scales, lower resolutions of the image. So the data is also very important. I mean, the way I see it, when you have a data-driven attack to a problem, when you define the problem, as soon as you define the problem correctly, you are halfway through. So you have already solved the problem by 50%. The rest is a selection of a proper data set, proper data, preparation of it, and then coming up, handling the art of making the network learn this data. So we use synthetic and real data. Our synthetic data is not really artificial, totally artificial. We used Kaggle's Galaxy Zoo images and applied simulations on top of them. And we also needed to label a little bit of real images for two purposes. One, for fine-tuning whenever necessary, but secondly, and more importantly, to be able to evaluate on real data. For that, you need labels. Yeah, synthetic data generation, I try to go over it quickly because there is too much stuff to talk about. Oops. So here we get a single Galaxy Zoo image. We have two branches, and this is the IT, basically the transient image. So we add it to one of the branches, to one of the images. So this one, this one is the transient that we are looking for. And then we randomly generate two PSFs, apply to the two branches, convolve them. And here we add random sky and Poisson noise. And also the transient image goes through the PSF2. So these are the three images that we need. This is a single sample for the network. Image 1, image 2, and the ground truth. For real data annotation, I will go over it very, very fast, but it was a kind of a scientific task, basically. So I cropped out the transient from the image, from a neighborhood of the image. Then we modeled the background, because usually the supernovae in this task were lying on the context of galaxies. I don't know if I'm using the right terms or not. So we modeled the background or the galaxy, underlying galaxy, with a polynomial of degree 8 and deducted it from the image to come up with the transient image. That's it. These are our ground truth images for the real task. These are some qualitative results. So reference or template images, science images. This is the state-of-the-art method. This is the state-of-the-art method after 5 sigma thresholding. And these are our results without any thresholding. You can already see how clean and accurate our results are. Well, this method is also, of course, I wasn't that fair. I have chosen more or less some good examples, but you see that many false positives are remaining in the difference image here, while our method has successfully eliminated them. Here we have even more interesting ones. So you see big artifacts here, and the method has been able to easily remove them. So these single dots that you see are the transients that we were looking for, and you see no noise here. And so multiple transients. It was very nice, surprising to see that it works also for multiple transients in a single image, because we had trained only for single transients. It also worked on cosmic rays. Ashish suggested us to add some cosmic rays as single pixels to the images and see how it works. And it worked perfectly well. It just removed them. The things that you see are the transients among the cosmic rays. So for numerical evaluation, we have precision and recall. These are the definitions. More or less, this has to do with contamination in the astronomical community, and this is about completeness. And here we again got surprised because these do not look like real precision recall curves. You should usually see such a thing, really a curve, not a corner. This means that the network has been quite sure whenever it has announced that there is a transient. So it either does not see it, or it sees it with a very, very high confidence. So for example, here you see that it cannot do better than 50-something%, and here anything above 78% has not been detected, no matter how low you bring your threshold. Let's see how this has happened. So I mean, basically the output of the network was supposed to be something like a binary, although it encapsulates also the amplitude of the transient. But for generation of these curves, we needed to scan over some variable, which is a threshold usually. So we started thresholding the images, the output images, and you see how far we needed to go down to see some noise really. So if you go down to under sigma over 100, you just start seeing some noise. And this is the reason for that specific behavior of the precision recall curves that you see. So in the other methods, if you remember, if you recall, they put the threshold on 5 sigma. Around 5 sigma, we have only the ground truth, basically. So the results. So first one is synthetics on synthetics, which is 100%. I mean, it works ideally. Transfer is when we have trained only on synthetics and it has not seen the real data at all. And it still performs reasonably well, like 54% of the transients are detected with a precision of 88%. And if you just fine-tune with a few samples on CRTs, on Catalina data, you get 76% recall with 98% accuracy. So a bit under the hood, this is the loss curve of the while we were training the network. So one interesting observation was that this wouldn't fall actually. This would continue at this level if we didn't do a specific trick. So up to this point, the network has learned only to generate blank images. So what we were asking from it was a blank image with a dot on it. So that was too small, it wouldn't learn it. But here we found that we should somehow boost the signal. And it was a very, very simple trick. Multiply the output or ground truth by a big number. That is going to boost the positives and keep the zeros at the zero level. So you will have basically you will, I mean, there is an idea behind it. You are increasing the learning rate only for the region that you are interested in, which is the region that is non-zero in the ground truth. And it suddenly started to learn what we are looking for. And as you see, the transient is appearing here. And if you let it go, you will have a much clearer transient in there. So deeper under the hood, actually I just did this slide. This is the very, very first layer of the network. And these are the feature maps. So I passed a pair of images to the network and I captured the output of the first layer. So basically you shouldn't see a lot about the idea about what the network is doing, but it was surprising that you can already see some things here. For example, I don't know how visible this is. There's a texture here, which I assume this is feature number 19, kernel number 19, has to do with the noise in the image. So it has captured the noise mainly and discarded the objects here. So this is the legend of the color map. And this is even more interesting. So this is basically the transient that we were looking for. And this filter already knows how to neglect or ignore the transient. I mean, I would be interested to find the filter that does the opposite of this. But this is also already informative. So this filter knows how to discard this transient from the other objects in the scene. So here I came up with an idea with Kai actually for the workshop on the last day. If anyone is interested, we can start going deeper in visualization of this network and find the kernels that are being triggered for finding a transient, perhaps seeing if we can do any science with it, or if we can find any physical properties in these kernels. Later we can talk about this. So currently what we are doing, so TransiNet 1 on ZTF data, which is out quite recently, worked just out of the box with a reasonable performance, like 40-50% of the images of the transients were detected. But with fine-tuning on 10 to 20 snapshots, it came to up to the accuracy and performance that we were getting on the Catalina data. So it means that with 10 to 20 snapshots and fine-tuning, we can adapt to any data set. We don't need a high number of labels. And multitask domain adaptation is my current future work, which will make it possible to adapt to any data set with 0 labels. And so this is the latest results I got last night, that this works on ZTF raw data, 3K by 3K matrices with 0 to 65K range of data, pixel values. And we are also using some tricks to even go deeper into the space and detect more. Yeah, these are the future works, and thank you.